This course will be taught in English, but you are free to speak French, and I can even reply in French if you want. So I'm the teacher, UCLouvain. The teaching assistant will be Mathieu Pigaglio. This course is about distributed systems and algorithms. Let me first explain the organization of the course. So there will be one lecture every week on Tuesday, except next week. Next week the lecture will be on Wednesday in Bathroom 21. At the same time. Of course, you know why this is the case. If you don't know why, I will tell you that it is a holiday on next Tuesday, September 27th, Fête de la Communauté Française. So the slot for the lab session, I will teach the course. The labs are Wednesday at 16:15, but not every week. So next week, the lab session, I will actually teach the second lecture, okay, and there will be no lecture next Tuesday. In general, there will be not so many labs. There will be two kinds of labs, preparing for the midterm and preparing for the project. Okay, so in this course, there's not going to be a lab every week. There will be maybe only 5 or 6 labs, plus the project. Okay, so for the rest of the course, there will be a midterm worth 5 points, which is optional. You don't have to do it. It will be around week 6 or 7. I will fix that with you later. There will also be a project, which is also worth 5 points. But be careful, this one is mandatory. You must do it. Well, if you don't do it, you'll get 0 points, of course. I can't force you to do it, but I strongly recommend it, because if you do a good project, you will already have 5 points on the final grade. Okay, so this is mandatory and counts for the final grade. And the final exam is in 2 parts. One part, which is worth 5 points, which corresponds to the midterm. So I will take the maximum of those 2, which means if you do very well on the midterm, and the project, you have basically already succeeded the course. Okay. So in my experience, this works really well, because the exam period is a very stressful period. If you do well in the midterm project, it very much de-stresses. And I'm happy because my goal is that you learn the stuff in the course. So if you already learned it for the midterm, I'm actually very happy already. Okay. There's also a 10-point part of the exam, which does not correspond to the midterm, but will correspond for your final grade. So basically you have 10 plus 5, the maximum with this, plus 5 for the project. Okay, so that's how the course is organized. The project will be done in groups of 2, and we will organize that in the final part of the course. So this will be in the last third of the course. Okay? That's the organization. This course is going to be about distributed systems, distributed algorithms, and let me give you a small introduction. There will be 2 parts to the course. The first part is a more formal part, where I will talk about small distributed systems with fixed number of nodes. And in the second part, I will talk about large distributed systems with a dynamic number of nodes. Okay? This first part is very important because we will see all of the formal, precise concepts, and then we will generalize that to real big systems on the internet, which is what everybody likes to do these days. So this is very important, but you have to know the basic stuff first. Okay? So that's basically the organization. The first part is based on a book called Reliable Distributed Programming by Rashid Garoui and Luis Rodriguez, two guys who I know very well. They're both very nice and very smart. There's also a second edition which adds security and a third author, but I'm not going to talk about security so much. So we're going to see a part of this book in the first part of the course. This is probably the best book. It's the best book I know on really understanding distributed algorithms and systems. Even the real complicated algorithms are explained in a very nice, layered way, so they're easy to understand. So these books are not really mandatory, because all the information is on the slides, but they are still very useful, and they say many things, and they give lots of intuition, so I will pass them around. So I recommend them if you're interested in the material and if you want to really understand the details and so on. But they are not especially mandatory, okay? So if you don't look at them, you can still succeed the course. Okay, so now I'm going to start with the content. What I want to start with is a teaser. I want to give you some intuition, some basic ideas of what we're going to be talking about in this course. And then we will have a formal part. So the first part here, it starts, actually it's pretty formal, but there's a lot of intuition. Me personally, I like to be very precise, so these will have very precise definitions, but I also want to give you intuition. Okay, so I don't want you just to memorize these things. I want to give you the intuition on how this works. Okay, so during the course, I'm going to also give a lot of intuition. And today, I'm going to start with a teaser, which is a little bit giving intuition. Okay. Okay, so let's start with the teaser. But before I start, I want to pause for a couple of seconds to think about the people in Ukraine who are fighting for their freedom and ours still now after 6 months, and they seem to be doing very well. So I want to give them as much encouragement as I can. Okay. So what is a distributed system? First of all, what does it really mean? So here's a guy that maybe you've seen before, Leslie Lamport, probably the most influential person in distributed systems. He invented many systems, many algorithms. Consensus, which is one of the motors of the internet, which we will see in this course. The most important consensus algorithms were invented by Leslie Lamport, an algorithm called Paxos. And also he has written a piece of software that some of you have maybe experienced. I don't know if you've ever used LaTeX. Well, LaTeX was written by Leslie Lamport on top of TeX. So the guy is theoretically very strong, but also very practical. So what does he say? Well, a distributed system is a system in which the failure of a computer you didn't even know existed can render your own computer unusable. Okay, so what does it mean? You have a big system with many computers talking to each other, and you don't even know that some of them exist. And if one of them fails, you can't do anything anymore. Okay, so this is kind of a joke definition, huh? But unfortunately, this is still sometimes true. It's maybe less true nowadays than 20 years ago. But here's a more precise definition. A set of computing nodes connected by a network which appears to the users as a single system. So basically, the nodes are somehow talking to each other and providing a service or an abstraction together, okay? And the user does not see that there's many nodes. The user sees a single system, okay? Okay, so that's what this course is going to be about. And we're going to look at this very precisely, and we're going to look at the internet, which is the most used and the biggest distributed system. And we're going to see exactly what you can do and what you cannot do, okay? This is something that Google and Facebook will not tell you, so I'm going to give away some of the secrets of these big systems that people will never tell you, especially the marketing department. Okay, so we're going to talk about the concepts, the models. So how do you model reality? This is all based on physics at the end of the day, yeah? But how do you model it, and the foundations? Okay? Okay, so that's what we're going to do. I want to give a little bit of motivation. So why are distributed systems important? I'm not sure I have to say so much there. It's clear that everyone's always using them. The internet, the web, small devices, mobile phones, little sensors, they're all connected together. So clearly, it's something that people use all the time. And people don't realize what the limits are and what the possibilities are. Okay? So it's very important, technically, to know how you make these systems scalable, because they can be large, reliable. Our nodes are always failing. Computers always fail, huh? When you work with computers, you never really rely on them, huh? Distribution, they're always connected together. Okay, so that's very important. So here, for example, is a photograph of a database with lots of racks and so on, okay, which is important. But there's also little smaller systems. Here is a very, very old thing, 1981. This was the space shuttle. There were 4 separate computing nodes in here, 4 computers doing exactly the same thing. And there was a voting mechanism. So those 4 had to agree completely. If they all agreed, then we know that the answer is correct. Okay? If you have 3 out of 4 agreeing, it's still good. Okay? But actually, it turns out in practice, if you have 3 out of 4 agreeing, the engineers already start to panic, because if one of them fails, maybe the second one will fail too. Okay? Even though it's still working. But this actually works very well in practice. Okay, so both big and small distributed systems. Okay, now distributed systems are very challenging. They're the most complicated systems to program, and there's 2 reasons for that. One is they can fail, and they're always failing. And that's normal, okay? Failure is a normal thing that happens all the time. It's not abnormal. It's not like when your computer crashes and you're upset. In a distributed system, it's quite normal, especially when you have lots of nodes. There's always going to be nodes failing, okay? And the system has to keep working. So it's not just failure, it's what's called partial failure. That means if you have 100 nodes, maybe some of the nodes will fail. Okay? Or the network has some problems. Messages are dropped. Maybe there's some interference. Radio waves or electrical impulses, whatever. Messages get corrupted, dropped. That's also failure. That happens all the time. So in a distributed system, failure is happening all the time. And the system has to keep working. Now you have to program that. You can imagine it's not easy to program that, huh? And it's not just failure. It's failure plus concurrency. And if you've taken a course on concurrent programming, you know it's complicated to make it correct, because you have non-determinism, and all the nodes are executing in parallel, and so you have to make it all work together. And it's much more than just a regular concurrent programming. You've already done concurrent programming, I hope, because if you haven't, this course will be even more challenging. So I hope you have some experience. But in this kind of distributed system, you have an extra complexity. You have messages that are asynchronous. It means you do not know the travel time. When a message goes from one node to the other, how long will it take? Well, you can't really predict it very precisely. It can vary a lot during the execution. So it's kind of non-deterministic also. So it's not just the scheduler, it's also the messages are non-deterministic. Okay? So just by itself, this is complicated. Now you add this plus this. Okay, and you have to program the system that keeps working when you have this, partial failure and concurrency. It's actually not easy, okay? And probably these are the most complicated algorithms, complicated in the sense of resisting lots of real-world hostile behavior. Most complicated ones that you'll be writing, okay? And that's what we're going to do in this course. So how do you do that? Well, you do it very carefully, okay? We're going to start, we're going to build systems into layers. We're going to make very precise definitions. Because depending on exactly how the system works, how much time the messages take or something, or how fast the nodes are, depending on exactly what the model is, the algorithms can be either very simple or very complicated or even impossible, okay? Some kinds of algorithms are even impossible to do, you can prove it. Okay, so that's kind of what we're going to do. I just want to say one thing. There is something called parallel computing, which is not the same as distributed computing. This is what scientists use when they do large simulations, calculations in quantum mechanics or whatever, or big celestial mechanics, or huge calculations with thousands of compute nodes. This is not the same as distributed computing, because in a parallel computer, there is usually no partial failure. Okay? In the parallel computer, you only have nodes executing parallel. You only have this part. So in a distributed system, when the nodes are far apart and they're connected through a network which can be very large, you also have this. Okay? So parallel is actually much simpler than distributed. Okay? So we're not going to talk about parallel in this course. I just mention it so that you can see the difference between the two. Okay? So how do you solve it? Well, we're going to start today. Question?
Yes, I saw that in the second quadrimester there is a course on cloud computing.
Yes.
Is there any...
Oh, there is definitely, yeah. Cloud computing is basically the kinds of systems that you find inside of data centers. Mm-hmm. So typically large databases, analytics, okay? But this course is much more general. We're going to talk about systems that run on open internet, whereas cloud computing will focus on tools that exist inside of data centers. So it's more like parallel. The big data is very parallel. Big databases, large databases are kind of parallel. So the cloud computing is kind of a subset, okay? But it's focused on specific tools. So I'm not going to talk about cloud, big analytics tools, okay? I'm going to talk about things like BitTorrent, or content distribution, or peer-to-peer in general. But in cloud computing, you will see the analytics tools. But the same concepts you see in this course, of course, they also apply to that course. So taking this course will help you understand the limitations of cloud tools. So I think the cloud course is not so formal as this one. There won't be so many formal definitions of distributed systems. So if you take this course, you will have a better understanding of the limitations of cloud tools. Okay? But I'm not focusing specifically on these tools. But in the cloud computing course, you will do projects using cloud tools. Okay? So the two courses are kind of complementary. Okay, so how do we do this? Well, let's start. I want to start by showing some examples, giving you some intuition. And the way to solve this very hard, is to look at some basic problems, which are called core problems, that always appear, okay, and see how to solve them. We're going to then first look at some core problems, okay? And let me give you a simple teaser problem. This is the two generals problem, or n generals in general. You have two generals. So here's the landscape. You have one army here with General 1. This is the landscape. You have another army with General 2. You have the enemy here. And they want to attack and win. And there's no radio or anything. And the only way they can talk to each other is by sending messengers who run very fast between the two generals. And they need to coordinate their attack. Okay? And that's the only way they can win. They only will win if they attack simultaneously at the same time. So they have to agree on the time. And they communicate through messengers. And this is like in the olden days, in the medieval days, or in Byzantium, okay, when there was lots of armies and generals who were always attacking each other. So they have messengers running between the armies. But the messenger is not very reliable, you know, he might be captured or killed or whatever. Or maybe he's a traitor or whoever, whatever can happen. So the messengers are not very reliable. Sometimes they disappear, okay? So how do we solve that? This is kind of like a distributed system, huh? The two nodes, they need to agree. And the network is unreliable. They have to agree. So agreement is like a core problem. Huh? So let's try to solve it for two generals. Okay? So how do you do it? Well, for example, General G1 will send a messenger, says, I want to attack at time T1 to G2. Okay, fine. And G2 receives the message, maybe receives the message, or maybe not. How are we sure that G2 received the message? Well, G2 can acknowledge the receipt. And when G2 receives the messenger, he sends another messenger with an acknowledgement. Says, yes, I have received your time. I'm good, we can attack. But is that really a solution? What do you think? Well, the acknowledgement also goes through messenger, so maybe it disappears. How can we ensure that G1 has actually received the message? So G2 sends the acknowledgement, but how can G2 be sure that G1 receives the message? Well, G1 can send in another acknowledgement back. You see where I'm going here, huh? G1 can acknowledge the receipt of the acknowledgement from G2. But that acknowledgement can also disappear. You see there's some kind of problem here, huh? You see it, you feel there's a problem here, huh? There's some kind of a problem. And you can formalize that. But intuitively, you can see there's a kind of a problem. Well, it turns out this problem, if you formalize it, this is the consensus problem in an asynchronous distributed system. You can prove it's impossible. That means it does not exist an algorithm. Well, okay, this problem is impossible. That means certain systems, distributed systems, certain kinds of algorithms are not possible. So we can't just do anything. So this makes it hard, okay? What do you do? Well, this specific problem cannot be solved, okay? So what can you do? So to make it, to recapitulate this, in a distributed system you have two nodes communicating through an unreliable channel. And those two nodes need to agree on a value, which is the time of the attack. And any message they send can disappear with some probability. It's not guaranteed the messages will appear. Well, an algorithm to do this would have to guarantee agreement in finite time always. Otherwise, it's not an algorithm. Maybe you could solve the problem 25% of the time in certain cases. It's not good enough. Okay? So agreement, this is called agreement. This is a core problem. You can see this is important. So in real distributed systems, this is a thing. This is a real problem. And we need to find a solution. So we have to change something, because in this particular case, it doesn't work. Okay? Doesn't work. Okay? Okay, so formally the algorithm is called consensus. So consensus is one of the core problems of distributed systems. Agreeing on a number, on a value. And in general it's like this. You have a set of nodes that can talk to each other, send messages. All nodes propose a value. G1 says T1, G2 says T2. Then you run the algorithm, but while the algorithm is running, the network might be unreliable, some nodes might crash, but despite that, eventually, all the nodes must agree on the same value. Okay? So what does it mean? Well, there's three formal properties. Okay? So some of the nodes crash. Well, if the node crashes, we don't care about that node anymore. So the node that does not crash is called a correct node. Okay? So some of them don't crash. So all the correct nodes must eventually decide. They must pick a value. Eventually means in finite time. Okay? They all must decide the same value, of course. Otherwise, it's not a consensus. And they only decide values that have been proposed. Otherwise, it's easy, yeah? They all decide on 0. Well, what if nobody proposes 0? Then you can't decide on 0. You have to propose on a value that was actually proposed. So that makes it hard. These three properties together makes it hard, okay? This is a hard problem. How do you make an algorithm that does that? Okay? And this is a very important problem. And so there's many, many, many examples of this. I just give a few examples. Here is a database, for example. A bank stores the money you have in your account. And for reliability, the database, there's 2 copies of the database, separated by some distance. Not even in the same building, okay, because the building might burn down, and that's the same failure mode. So the databases will be geographically far apart. It must be far apart. And you update your account. Both of them have to agree on the new value of your account and on any change. So if you make a transaction, okay, it's a kind of consensus. This is called atomic commit. This is part of a transaction. When you update a database, you atomically change the value. But if I have 2 copies of the data, the transaction is a distributed transaction, which updates both of them. And of course they have to agree. And the transaction is either committed or aborted. If one of the copies commits, the other one has to commit. You can't have one of them committing and the other one aborting. So the 2 proposal values are commit and abort. Seems very simple. But the transaction either commits on both copies or aborts on both. And if that's the case, then the values will agree. Okay? You see that? So this is a simple example, but in many cases, you need nodes to agree on things. This is what we're going to see in this course. And you can see it's not so simple, because if the network is asynchronous, so there can be failures and we don't know the travel time. In an asynchronous network, a message takes any finite time. But we don't know what. finite time. With this system, this algorithm is impossible. Well, that's not good enough, of course. In the real world, we have banks and we need to do something, okay? So we have to find a solution to this. That's something we're going to see in this course, okay? So that's a core problem, consensus. It's one of the most important problems. Okay, here's another problem, which is called atomic broadcasts. This is a different problem. I'm now sending information, okay? I'm sending information. A node broadcasts a message. But there's different kind of broadcast. This is what's called atomic. So in this algorithm, so first of all, if the node which is sending is correct, if it doesn't fail, then all correct nodes will deliver the message, which means the message arrives and they give it to the application on the node. Okay, that's pretty reasonable as a property, Of course, all the correct nodes deliver the same messages. That's pretty reasonable because you don't want to invent random nonsense. They only deliver the messages that have been sent, the same ones. Okay? And it's atomic. This is what makes it a strong algorithm. The messages are delivered in the same order. Okay? This is very important too. Because let's say I'm doing transactions again on database, and one transaction adds 10 euros to your account, and the other transaction adds 1% interest. Well, the result will change. If you do it in one order, the 1% will not see the 10 euros. But if you do in the other order, the 1% will see the 10 euros and will give you 10 cents more. Okay? So in order for this to work, you have to deliver the messages in the same order. So you can see this again is an important algorithm. In the real world, the order matters. Okay? Very often it matters. Okay? Now, I've shown you now two core problems. Okay? Consensus and atomic broadcast. And now I want to give you an example of the kind of reasoning we do. It's still a little bit intuitive, but it's an example. It turns out, so these two core problems, it turns out that they are equivalent. You can prove that they have exactly the same power. It means that if you have one, you can do the other, and inversely. Doesn't seem very obvious, huh? But I have to understand this algorithm, this is very important. Okay, so atomic broadcast is equivalent to consensus. So what does that mean? It means that if I'm given atomic broadcast as a library, I can use it to solve consensus very easily, okay? But I can use it in a straightforward way to solve consensus, and conversely. So here's how it works. So remember what consensus means, huh? Every node proposes a value, the algorithm runs, and they all decide, and they have to decide on the same values. Okay? So we can implement that using atomic broadcast. So every node broadcasts its proposal. Now remember the property of atomic broadcast, that all the nodes receive the messages in the same order. That means they will receive the same first message, okay? That means the nodes will all receive the same first message. That means when they receive the first message, they can just pick that as the result of the consensus, okay? And this satisfies the properties of consensus. That the value has been proposed, that they all agree on the same value, eventually, in finite time, okay? This is satisfied here. So you can see that if I give you a library that does atomic broadcast, you can use it to implement consensus. Okay, that's You can understand better. This is still kind of intuitive. Huh? I've not given you the code or the formal argument yet, but you can see intuitively that it will work, huh? And it will work. What about the other direction? Assume I give you a library that can solve consensus. Remember, consensus, all nodes propose a value. The algorithm runs, and all correct nodes would eventually decide on the same value, which is one of the values proposed. That's consensus. I'm giving you a library that does that. It's done, it's implemented, tested, debugged. And I'm telling you, you can use it to solve atomic broadcasting. So how? So whenever I put a little d here in the slide, it means that you guys have to tell me the answer, that we discussed something. So what do you think? Does anybody have idea here? If I have a consensus, how can I use it to solve atomic broadcast? What do you think? How, remember atomic broadcast, all the messages are received in the same order. Okay, all nodes are broadcasting, and all correct nodes, so nodes that don't fail, the messages will be delivered, and they will be delivered in the same order. That means if two nodes at the other side of the world broadcast A and B, who knows that every other node will receive A, B in the same order, no matter where they are. Okay, that's atomic broadcast. How can I do that if I have consensus? What do you think? Any ideas? Anybody have an idea? A wild idea? How do you implement atomic broadcast using consensus? Yeah?
So, sorry if I understand well, if all computers have consensus on a given value, we can show that we can make in sort that messages are received in the good order. That is what we.
That's what I'm asking you. You have to tell me how it's possible.
Okay.
Yeah. So I have a consensus algorithm, which is, so there's a piece of code running on every single node, okay? All together, that is the consensus, and each node can propose values, and the algorithm runs. And each node will also decide values when the consensus runs. And the decisions are going to be according to the property of consensus. It means that every node will decide eventually. It will be a proposed value, not just some random number that is decided, and they all decide on the same value. And then if you run consensus again, the same thing will happen again. Okay. So essentially, it's a sequence. You can actually do many proposals, and you could have many decisions. Okay.
I'm sorry, but I don't understand. It is which kind of problem? Like it is a problem like incubation.
So I have given you a library that solves consensus. You have the running code.
Okay. So
I want you to give me a library that solves atomic broadcast.
with the library that solves consensus. Okay.
No, I have given you the library that does this, and you can use that to make your life easy. But what you have to give me is another library that solves atomic broadcast.
Okay.
So how do you do it? What do you think? What's the idea?
We can use the library of consensus to build a consensus about the first message.
Okay, how does that work exactly? Be more precise. What is, in both algorithms, there's something that is the same for all nodes. What is the same for consensus, and what is the same for atomic broadcast? Once you know that, you can try to somehow map these two sameness things. Okay? Yeah?
If we have consensus, we can agree on the value, and the value we can use for atomic broadcast is the order in which the message are received.
Yes, very good. So the consensus, you propose a value, but a value can be anything. It can be any data structure. So in this, we will use, what we will propose as a value is a proposed order of reception of atomic broadcast. We receive C, then B, then D, then X, okay? And all nodes propose an order. We run consensus, and the decision will be one of those orders. And that will be the order that atomic broadcast will use, okay? You see, so the same value of consensus, the value will correspond to an order of messages. So the value will actually be a sequence of messages, or a partial sequence, huh? It's not just a number. You see, a value can be any data structure, of course, huh? It can even be a list of messages, okay? You see the idea? This is, I'm just giving you intuition, huh? But we can make this more precise, of course, huh? So, two algorithms that seem to be very different on first glance are actually equivalent. So you can see that distributed algorithms, it's not so simple, okay? There can be algorithms that look very different, but they're actually the same. But there can also be the opposite case, algorithms that look the same, but they're actually very different. And one of them could be impossible, okay? Like the consensus in an asynchronous system, okay? Okay, so atomic broadcast is equivalent to consensus. So this is just an example, huh? I'm giving you intuition here, and I'm showing you the way you have to think for this kind of algorithm, okay? But in the rest of the course, we will make it more precise. We will make everything be formula. So try to understand the intuition today. It will help you a lot with the formal parts. Okay. Okay, now let's talk about another part of distributed systems, which is the concurrency. The messages traveling between. You have all these nodes running at the same time, sending messages, okay? And in the two generals problem, actually, the system that they run on, so this is like a program, okay? And it's running on a system underneath. And the system in this case is called asynchronous. The A is very important, eh? Asynchronous means that when I send a message, there is no bound, no upper bound on the time to deliver a message. Now, you have to be careful to understand what it means. If the message arrives, it will arrive in finite time, but there is no fixed upper bound on that time. Okay? It could be arriving after 1 millisecond, or maybe sometimes it takes 20 milliseconds, sometimes it takes 5 seconds. Actually, the postal mail is kind of like this. Maybe you read an article sometimes in the newspaper where a letter that was posted 50 years ago finally arrives. Have you ever read it? Occasionally you read articles like that. Someone gets a letter that was sent 50 years ago. That means the postal mail system is actually pretty much an asynchronous system, okay? They say the letters will get there in 2 days, but sometimes it takes 50 years, okay? This is the most free kind of distributed system, with the least constraints. It's one particular kind of system called asynchronous. And also there's no bound on the compute time. So we have actually 2 times. We have the message traveling on the network, but we also have a computation on the node. So it receives a message, it does a computation, sends another message. So in an asynchronous time, there are no bounds on this, no upper bounds. They're still finite, huh? So you have to understand carefully. It's still finite. I'm not saying it's infinite or something like that. Huh? No. So if the message is not dropped, if it actually is delivered, it will be delivered in a finite time. But there's no fixed upper bound. Okay, so that's called an asynchronous system. Well, unfortunately, life is tough. It turns out the internet, the system we all know, we love very much, it's essentially an asynchronous system. It's designed as an asynchronous system. There is no, in all the algorithms, basically IP, yeah?
If we have a system with different embedded devices that run with a real-time operating system, does that still count as an asynchronous system?
Well, how are the messages transmitted in this senior system? Is it clocked? There's another kind of system where you have bounds on the messages, huh? If those embedded devices are sitting very close to each other, and there's like a common backplane or something, then you can have some kind of bound. Huh? But if they're kind of far away, if one of them is in Japan and the other one is in space or something, is your system like that? Can one of the nodes be on a satellite and the other one is sitting here in the room?
Yes.
Yes?
So the operating system doesn't really matter, it's the communication.
Well, that means your system will be asynchronous in that sense, right? There's no bounds. Depends on how far away the nodes are. There might be routers in between, right? Okay, but it's more subtle. We will talk more about that. It's actually very subtle, and you're kind of going towards some of the subtlety. So the internet is essentially the way it's defined, using IP, yeah?
Can we have bounds, but probabilistic bounds, like 99%?
Ah, there we go. Okay, a probabilistic bound. Yes, you can have probabilistic bounds, but that means your algorithm will only be probabilistically correct. Okay? That's not good enough for a bank, okay? If I put 10 euros in my account, it will arrive with 90% probability. I don't agree on that, okay? So sometimes it's okay, probabilistic. Yes, and if you look at there's different kinds of asynchronous, because the internet is based on laws of physics, and we'll talk about that later on. So, yeah, you're also getting toward this. So the idea is that the internet is essentially asynchronous, but this is not good enough. If we accept this, then we can do nothing. Okay, then we can go home. We can't do many algorithms. We cannot do consensus. So this is the way it's built. It is using IP, using hierarchical routing and so on. There is no time bounds built into the internet. Okay, so algorithmically, physically, it is essentially asynchronous. But in practice, maybe we can say something, but we'll tell you that. But so far, it's asynchronous. Okay, so that makes it very hard, the internet, huh? And we know this is what we saw with the two generals. Consensus cannot be solved in an asynchronous system if a single node may crash. So if I have n nodes, some number n, 100 nodes, they all propose values. It's running on an asynchronous system. So no bound on the message time, no bound on the compute time. For such a system, consensus cannot be implemented. It is impossible to implement consensus, okay? And you can prove it mathematically. And it's a famous result, in fact, called FIB. This is a famous result proved in the 1980s. And people were very upset when they saw this, okay? They said, shit, what are we going to do, you know? We can't do it. But there was a guy sitting in the background who actually came up with the solution. It's the guy you saw before, Leslie Lamport, okay? But we'll see that in a little bit. So this, of course, is a very important impossibility result. If this is the only thing we can say, then we're stuck, okay? We cannot build distributed systems that are asynchronous. And the internet is asynchronous, so something has to change, okay? So if this is actually true theoretically. If the internet really was asynchronous, we could not do consensus. But somehow we cannot accept that, okay? Okay, so that's asynchronous. So I've now explained to you one extreme, the worst kind of distributed system, which is an asynchronous. It's kind of the worst one. It's the one that's the hardest, okay? But it's not the only one, as already someone was mentioning. There is another kind of distributed system, which is much nicer one. It's another extreme. So these are the two extreme cases, huh? On the one side you have asynchronous, where algorithms are very hard and there's many impossibility results. On the other side you have synchronous, which is much nicer, but of course you pay a price. When things are nice, you always are paying a price, huh? So a synchronous system is a system where you do have the bounds. There is an upper bound. The two nodes, I guarantee that the messages will be arriving in 10 milliseconds or in 100 microseconds. And when I do a computation, it will always be less than 1 millisecond for guarantee before it sends another message. If I know the bounds, the system is called synchronous. Okay? And this kind of system is a very nice system for writing algorithms. But it's a very hard system to implement. Okay? Basically, in order for a system to be synchronous, it has to be very small. Okay? A LAN, local area network. Let's say you have Ethernet, but only one cable. The two nodes, you have some maximum distance, so you know an upper bound. Okay? Or a cluster computer where you have a bunch of processor board with a back plane, which is the communication network, and they're very close together, just a few centimeters. Okay, so the LAN may be a LAN you can guarantee less than 1 millisecond on a single cable Ethernet. Not if you have routers there. And a cluster, of course, can be much, much faster than that. The communication can be done sometimes in microseconds as the bound. So this kind of system are essentially synchronous. And it means it's much easier to write algorithms. And again, let's see how it works. So let's go back to consensus now. In a synchronous system, you can do consensus, and even when up to n-1 crashes, it'll still work. If I have n nodes, for some n, 100 for example, and I run consensus, it will work for any number of crashes up to 99. Of course, you have to have one node running, or else it doesn't mean anything, huh? But up to n-1 crashes, you can run the consensus, and it will run, and it will work. So this is much easier, okay? It's much easier to write algorithms, but unfortunately, it's much harder to implement. You see that you're seeing now the fundamental trade-off. The things that are easy to implement, the algorithms are hard or impossible. The things that are hard to implement, like a synchronous system, the algorithms are easy. Okay? Of course, everybody wants a synchronous system, but if you want a very fast synchronous system, first of all, it has to be very small. Second of all, it's going to be very expensive, okay? And very hard to make it. But of course, the algorithms will be easy, okay? So why is this? Why is consensus so easy in a synchronous system? It's because of crash detection. If I send a message and the upper bound is 1 millisecond, and if I do not receive a message in 1 millisecond, then I know for sure the message has crashed. I'm guaranteed because of the bounds. So a synchronous system has accurate crash detection. Every node, let's say for example the algorithm, every node sends a message to every other node. Okay? And if I don't receive a message, if I'm at a node, if I don't receive a message from a particular node within a bound, then I am guaranteed that that node has crashed. Okay? Why? Because the system is synchronous. And the synchronous has a known upper bound. So it's a mathematical result, okay? My crash detection is perfectly accurate. That means the consensus is very easy. I know exactly which nodes have crashed, yeah?
So you are assuming that there is a message every millisecond?
For example, some algorithms, they work like that. Huh? They do flooding, and every node is sending a message to every other node, and then every node knows what is the code running on the other nodes. Huh? It's one algorithm running. That means the code is distributed over the nodes, and every node knows what is the code running on all the other nodes. It's not unknown code. Huh? Yeah?
Did the bound of a synchronous system is always small, or can be?
It can be very large. For, let's say, you could turn part of the internet into a synchronous system. You just make very large bounds. What does it mean? It means your system is very slow. Very slow. So let's say within Belgium, the internet, within the routing algorithms in this geographic area, you are guaranteed that the messages will arrive in 500 milliseconds, maximum, okay? Well, just say that the bound is 500 milliseconds and Belgium has a synchronous system. But when you want to time out, when you want to do crash detection, you have to wait 500 milliseconds. That means the clock speed of your system is 2 hertz, okay? So your system becomes very slow. So the problem is trying to get fast synchronous systems. That's very hard. Many real systems that are almost asynchronous, you can turn them into synchronous by setting very high bounds. But there's no magic, you pay a price. You have now created a very slow synchronous system. Sure, you can write consensus, but it would be very, very slow. That's not acceptable, okay? So there's no free lunch. This kind of a no free lunch result, huh? You want your systems to be there, but going there, you pay a big price. You're always paying a price, either in money or in time, okay? Well, so we're kind of in a box now, huh? What do we do? Internet is kind of here, huh? And consensus is impossible. Well, cluster is here, but not internet. So yeah, cluster is fast, but it's a very small, localized system. So we're not doing communication over the world, okay? So this is a very limited form of system, okay? So we still are kind of stuck, right? We're kind of stuck here. Okay. So this result is not useful for the internet. Well, the internet is basically asynchronous, but you can kind of force it to be synchronous by setting a very high upper bound, which is not useful, okay? So you see there is some kind of a problem here. And this is something we're going to think about in this course. And there's a solution, okay, to this problem. So people have thought about this problem for some time, let's say since 1980 or something. When the internet starts getting big, people start realizing this. That this result here, the one here, this is from like early 1980s, okay? So this was a big problem in the 1980s. And so we need to make a solution to this, okay? And I will present you a solution, and the solution is what is done today. So there is a solution to this that is practical, that is formally defined, and you can write algorithms for it. They're not as good as this, okay? It's not up to n-1. They're not as good as this, but at least they're not impossible, which is, they're better than this, okay? This one. This, it's impossible. So this is very bad, huh? Whereas here, in a synchronous system, the algorithms are possible, but the system is completely impractical. And internet is not like that at all. Okay? And if you try to force the internet to be like that, it doesn't work. And people have tried, and there's strong reasons from physics why it cannot be synchronous. Okay? So there is a solution to this, but I will not say it right away. I will make a small break, and you will see the solution after the break. Cliffhanger. Okay? Before the break, so I'm going to continue now. Before the break, we saw that we have somehow a problem because asynchronous systems are basically impossible to use. The algorithms either are impossible or they're very complex. And synchronous systems, it's very easy to write algorithms, but they are completely impractical. You cannot build the internet as a synchronous system. So what do we do? Okay, this was the question before, and this was a big problem in the 1980s, and a lot of very smart people were thinking about this, and a solution was found, which is actually quite an interesting solution. Okay, and let me start by giving you intuition. Let's look at the internet now. Notice I told you the internet is essentially asynchronous, and this is correct. No time bounds are built into the basic algorithms of the internet. The larger you build it, the more routers, the slower it gets. There's no upper bound built in. Okay? But in practice, it's mostly synchronous. And this actually goes to a comment of one of the students, that there's some kind of probabilistic thing going on here. If I make a communication to someone else who is close to me, most of the time it will be fast. So let's say within the bounds of the university, let's say 1 millisecond, okay? Or within Belgium, 10 milliseconds. And most of the time it's respected. But occasionally it's not. So there's no real guarantee, okay? And why is it not respected? Maybe because of congestion. So what does congestion mean? It means there's a router between the source and the destination, which has a fixed buffer size. Too many messages come in, so some messages are dropped. So the router will drop messages if it does not have space. And congestion means there's too many messages trying to use that router. And an algorithm like TCP will see that, will time out, and will send the message again. Okay, it will resend in order to get a reliable byte stream. And so the result that the end user sees is that most of the time the bound is respected, but sometimes the time goes way up. And typically it's because of congestion, because at some point, routers, because many people use the internet, it's shared, it's a shared resource, okay? So can we formalize this? If we could somehow formalize this, and then we would use that formal definition instead of asynchronous or synchronous, something that's in between the two, taking advantage of this. Notice this also respects the laws of physics, okay? The farther away that nodes are, because you have speed of light delays, between Japan and here, the delay will always be longer than between here and Brussels, for example, most of the time. Because the distance is larger, and it's not just speed of light, there will also be more routers. There will be more levels of structure. So the internet is a hierarchical system. So if I am within the lowest level of the hierarchy, it will be fast. But if I have a congestion or there's a problem, I go to a next higher level, so I have to make a round trip. And there's different levels of hierarchy, and each time I have to increase the hierarchy, the system will be slower. But most of the time I don't. Okay? So for these reasons, we can say that for internet, it's mostly respected most of the time. Okay. So we're going to model this. So the question, how do you make a formal model of this that is simple, clean, that captures what's going on in a nice way, and that we can use so that we can build real algorithms? Okay? And this led to the definition of what's called a partially synchronous system, which sits somewhere in the middle here. Partially synchronous. Okay, it sits somewhere here. A partially system, so we will see a formal definition of this, but I can tell you what it is now. It's a little bit subtle. When you start running the algorithm, the system is asynchronous, and eventually it becomes synchronous. Okay, so it's actually kind of subtle. That means when you start running the system, there are no upper bounds. After some finite time, an upper bound will exist. But we don't know this time, but we know that there is a finite time. And we don't know the bound, but we know it exists. You see, it's a very subtle combination of things that are known and unknown. Huh? But it turns out to exactly capture this. That means when I'm running an algorithm, let's say the connection is 1 millisecond most of the time. Well, assume the bound is 1 millisecond. Fine. But maybe the real bound is 10 milliseconds, because after a while I'm going to have congestion and it'll be 10 milliseconds. That's fine. All that means is that you wait a little bit longer and the bound becomes 10 milliseconds. You see? So we don't know when it becomes synchronous, but we know it will become synchronous because algorithms take finite time, and the bound will not go up to infinity after that finite time. It will go up to some value, okay? So this definition captures the structure of the internet, okay? This is a fairly subtle definition, and now the question is, can we define algorithms that run on this model? So I told you that consensus, let me make a little diagram here. So here, consensus is impossible. Okay, you can prove that. Here, consensus is possible up to n-1 failure. Up to n-1 failures. Here it is impossible even if you only have one failure. Maybe, it's impossible. So what is going on here then? What about consensus here in this model? We will see in this model, in a partially synchronous system, you can write a consensus that works if you have less than n-2 failures. For less than n/2 failures. There's maybe a better way to say it. The majority of the nodes must be correct. The number of failed nodes must be less than half, a minority. If you have the majority of nodes are correct and your system is partially synchronous, you can implement consensus. So we're kind of saved, okay, by this definition, because this is what you can do for the internet. So actually, the internet is not really so bad as a real asynchronous system. The internet, you can actually model it partially synchronous, okay? It's not quite such a bad system as here, huh? It's actually modeled, you can model it here, and you can do consensus. So we're good if we do this, okay? Right? So what do you think? Is this good? So these three results are known, okay? Here it's impossible. Here it's possible up to n-1 failure, but if your system is partially synchronous, and the way I have defined it, and don't worry if you don't understand all the details, we will see this later. I'm only giving you now an overall view. Here consensus is possible if the number of failures is a minority, less than half. You need a majority of correct nodes. And in fact, because of the way the internet is built, it actually fits this definition. So we're saved, right? Are we saved? What do you think? Are we saved now? Are we? Is it reasonable, or are we saved, or are we not saved?
Well, it depends how many failures we get in the world.
Yeah, I mean, is that okay? Well, if I have 1,000 nodes, if I have less than 500 failures, what do you think? Seems reasonable. Usually, the number of failures is not so big, right? Even in data centers, you don't have so many failures, right? We're saved, right? What do you think? Am I putting doubt into your minds? Yes?
I think the internet can be thought of on a partially synchronous system, but only in certain patches of the internet. Because like, the bounds can apply to a certain part of the internet. It's not applicable to another part of the internet.
Why? Let's say I say that the whole internet is partially synchronous. Is that wrong?
It can be partially synchronous, but according to different bounds. You don't
Of
have
course,
the same.
yeah. So partially synchronous does not define the value of the bound. It only says the bound exists. It can be very high or very low. If I have a system running in one city or inside the university, then the bound will be low, 1 millisecond or less. So I'm good. I won't have a very slow system. I will have a fast system. But if I have my system be very spread out, then the bound maybe will be higher, okay? That seems reasonable, right? Does it seem reasonable?
Yes.
Yes, it is actually. Why are you doubting? Of course it's reasonable, okay? Is it the tone of my voice is making you doubt or something? I don't know. No, this actually is a solution. And so all of the big internet companies, Google, Facebook, or Meta, whatever, Twitter, all these guys, they are using these algorithms. They will not tell you exactly, of course it's proprietary. Google, but enough is known that we know that these algorithms, so there's famous algorithms. The one invented by Leslie Lamport is called Paxos. This was around 1990. But there are more recent ones that are the same power but are simpler. This is actually a complicated one. But it was the first time somebody did it, so it was an existence proof, okay? This is actually a complex algorithm, but there's a more recent one called Raft, which was invented in 2014, which has the same power. It's the same specification, but it's much simpler to implement, okay? So this algorithm is actually very complicated to implement. So the very smart, brilliant engineers in Google, even they have problems implementing this. And they admit it, okay? You can see an article. I can tell you. So in Google, there's this thing called chubby lock management. This is just a story, yeah? But there's an article on this used by Google. This uses this Paxos algorithm. And inside that article, it says that almost all implementations of Paxos are incorrect. And it's very hard to implement. Okay? This is Google engineers speaking, okay? So, but nowadays, it is correct. So the Raft algorithm implements this and is much simpler than Paxos. So this actually is now very practical. Now all the big internet companies, the billions of money they make is built on top of this, okay? If there's one algorithm that is like the foundation of the internet, it's this one, okay? And it used to be Paxos or some version of Paxos even if it was slightly buggy, but nowadays it'll be more like raft algorithms. So we will see rafts later in the course, okay? But you can look it up already if you want. So in some sense, the hidden structure of the internet, how come big internet companies can exist and make billions and have these huge systems inside of data centers with thousands of nodes, and it works. It works because of consensus. And it works because the internet is partially synchronous, okay? So this theoretical development, which was around 1990, early 80s, 1990, is very important for the practical internet, you see? Okay, so this actually, partially synchronous, is the foundation of all practical internet algorithms, distributed algorithms on the internet. It's partially synchronous, okay? And you already know it now in the first lecture. It's good, huh? I'm giving you lots of secrets here. Okay, so that's all I want to say about this now. Of course, we will come back to this in the course. Huh? This is just a teaser. I'm just giving you a little bit of hints that there's stuff going on here, okay? Okay, let me go on now. And we're going to build these algorithms. We're going to design algorithms. So now we kind of see how the hardest problem is solved. In practice, how do you write these algorithms? These algorithms are handling partial failure and concurrency in a partially synchronous model. It's still complicated, okay? They're still complicated, and you'll see. And the only way to do complicated things is to build abstractions and to make layers. There's no way. In the 1990s, people didn't do that. In the 1990s, distributed algorithms, books, if you take a book from 1990, it's a mess, okay? This book comes from 2007, and it's very clean and layered. So if you read this book, you get the idea that distributed algorithms is a very clean and layered discipline, very nice and logical in this book. Before the year 2000, it was not true. It was a mess because there was no abstractions. Every algorithm was a big, complicated thing with a big, complicated proof. And Paxos is no exception. Okay, Raft coming much later. Everything was complicated. And now we start finally to make things simple and clean and layered. Okay? And this book then is probably the first book that shows these algorithms in that way. So that's why it's still the best one if you want to really understand, okay? So the first part of the course will be based on this. So you will understand much more than even the best distributed systems researchers understood in 1990. It's nice to know, huh? Because of all the hard work that was done after. One of the abstractions is called a failure detector. So a failure detector is like a black box that tells you when that node has crashed or maybe has crashed. Okay? It's a component that detects crashes, and there's many ways to implement it, and it might use heartbeats. It means it's sending messages regularly, getting replies. There's many ways. And it might make mistakes, initially wrong, but eventually it's correct. Okay? This is exactly how partial synchrony works. Initially, you don't know the bounds, but eventually the bounds are known. Well, the failure detector is working in that environment. So initially it might make mistakes. It might say the node has crashed, even though it didn't really crash. But eventually, it will make no more mistakes. So that's nice. When is that going to happen? You don't know, of course. Isn't that nice, huh? There's so much ambiguity. Eventually, this failure detector makes no more mistakes, but you don't know when the mistakes stop. Just know that they will stop. So you have to write algorithms for that. Interesting, isn't it? Okay, so we will do it. Okay. So we will do that, of course. And all the complicated algorithms that we show in the book will be using failure detectors, okay? Because it makes them very simple. The code that I will show you is actually very simple. It'll be just one page of simple code for these very complicated algorithms. So that's the advantage of this book. The layered structure lets you show these complicated algorithms in a simple way, okay? Okay, let me now talk a little bit about failure. Failure is normal, I said. What kinds of failures are there? Okay, so that's a thing that has been studied. How do systems fail? Well, a typical failure is a crash. So everyone has seen crashes, okay? But there are other kinds of failures. And I will mention two other kinds of failures. One is called Byzantine faults, and the other is called self-stabilizing algorithms or self-stabilizing systems. So that's another kind of failure. So a Byzantine fault, it's the worst kind of failure. It's not just that the node crashes. It starts becoming totally weird. It can do anything. It can run any code, send any wrong information at any time, okay, a mid-message or whatever. So it's basically an evil genius is sitting in that node and is doing whatever that he wants, okay? Now, this is the worst kind of failure that you can imagine. And you can define it formally, a Byzantine, okay? It's explained in the second edition of the book, the one where it's reliable and secure. This one has now become very popular because of cryptocurrencies, okay? Like Bitcoin, for example, which has hostile nodes. And the reason why there are hostile nodes is because there's money involved, and the hostile nodes can steal real money in the real world, okay? So that makes there's an incentive for creating these evil nodes. And a Byzantine algorithm can resist that. You can actually define algorithms that resist evil nodes. It's not the same as here. The failures that I'm talking about here are just crashes, okay? This is just regular crashes. It's not the same if you have Byzantine. Byzantine, if a node becomes Byzantine, it basically becomes evil, and it's much harder for the other nodes to survive. So typically, you can actually define Byzantine algorithms, and they use cryptography, and typically, they will only tolerate up to 1/3 of evil faulty nodes, whereas the regular non-Byzantine algorithms tolerate half. So here you need a majority to be correct. In a Byzantine, 2/3 have to be correct, or more than 2/3, okay? It's like in an organization. If I have an organization with 100 people, and some of those people are spies, how many spies can there be and the organization still works? Well, in a Byzantine algorithm, you can have up to 1/3 of these evil spies, okay? And you can prove it still works. So that's another kind of algorithm. So this is really the worst case, huh? A Byzantine algorithm is a node that becomes evil and stays evil forever, okay? Now, self-stabilizing is a little bit different. In a Byzantine algorithm, or in a crash here, the node crashes, it's permanent. It crashes forever. Whereas in a self-stabilizing algorithm, the nodes temporarily go crazy. And then they get back to normal again, okay? So it's like a person having epileptic attack, falling to the ground, but eventually he wakes up and it's normal again. Julius Caesar was like that. Right? So this guy was like this, temporarily. Even regular people are like that. Every day, you are completely out of action for at least 8 hours. It's amazing, huh? But still life goes on, huh? I'm talking about sleep, huh? So this is temporary problems. This is a system where the nodes can temporarily go wrong and do arbitrary things, but after a finite time they come back to normal. Okay? And the algorithms that are based on these temporary bad nodes are called self-stabilizing algorithms. And the way to define it, so again you can do formal definitions, and we're going to do a little bit of that. A system with many nodes, it can be either in a legitimate or illegitimate state. Illegitimate if there's some nodes being crazy, but that's temporary, okay? And if you prove the code of the algorithm, you can prove two properties, convergence and closure. So convergence means if it's in an illegitimate state, it will eventually go to a legitimate state. You can prove that in the execution. And closure means if it's in a legitimate state, it will stay there. Okay? If your algorithm has those two properties, then it's a self-stabilizing algorithm. And such algorithms have been used, okay? And what is the advantage? It will handle any temporary failures, transient failures. If I kick the algorithm and it falls down, it will get up again. Basically, you can see like that. You don't need to initialize it. If you start up the system, it will start in a random state. That's fine, it will eventually stabilize. You can also compose systems. You can connect two systems, blocks together, and one system is like an input to the other one. But if the first one is in a weird state, eventually it will stabilize. And once it stabilizes, then the second one will also stabilize. So you can compose them. So these systems are actually very good if you're like on Mars, for example. You have a little robot running on Mars, and a cosmic ray comes in and flips a bit in memory. That's a temporary problem, okay? The system temporarily goes to a weird state, but if it's self-stabilizing, it will fix itself, okay? So these kind of systems can be useful. And here's an example. This actually was a real thing called token ring. It's probably still used some places. It was invented by IBM, but I think probably Ethernet has taken over, but this sometimes is probably still being used. So how does it work? You have a ring of nodes connected using a cable. And how does the node know that it's allowed to send a packet? It knows because it owns the token. And the token travels around the ring, and when a node wants to send a packet, it waits until it receives the token, and then it's authorized. And this guarantees that there will always be only one packet. Okay, what if there's two tokens? Or three, or zero? Well, the algorithm is actually a self-stabilizing algorithm, so any number of tokens different from zero, and eventually it will go back to one token. Okay, so this is actually a real example of a self-stabilizing system. Okay? Okay, so that's all about failure. We're going to talk much more about failure. I want to say a little bit more now about the two parts of the course. So I said one part of the course will be on small fixed systems. So this is where we learn all of the basic concepts. But of course, large systems also exist, and they are dynamic usually. If you have a very large system, like BitTorrent or some other kind of very large system, peer-to-peer system or gossip system, you have always the number of nodes is changing. Nodes are joining, nodes are leaving, nodes are failing. The larger the number of nodes get, the higher the probability of failure, of course. If I have 1,000 nodes, pretty surely one of those is going to be failing. Whereas if I have 10 nodes, maybe not. So these systems are dynamic and large. Large-scale systems are almost always dynamic, of course. If you have a large organization, the number of people will always change. How many people are members of the university community? There's no fixed number. Whereas a soccer football team, there will be 11 people on the field, guaranteed, always 11. So it's very different. This will be the second half of the course. So the second half of the course, we will talk about large systems, and it will be a little bit less formal than the first half, but still formal enough that we can prove certain properties. We'll talk about peer-to-peer, gossip, algorithms. I won't really talk so much about cloud computing because there's another course on cloud computing. I might talk about edge computing, very small, low-power devices sitting on the edge. And because they're small and low power, they fail a lot. These very low-power devices, maybe they run out of power, or the connectivity is very bad on Internet of Things. So this is a very big thing nowadays. It's growing exponentially faster than cloud. So the cloud is kind of maturing nowadays. So edge is growing very fast. And mobile phone is only a small part of that. So the number of devices sitting in the environment is growing a lot. In certain places more than in other places. But people have lots of home computing systems nowadays. So these are all distributed systems where you have a lot of failure and dynamicity. Okay? Okay. So, yeah. So we're kind of getting to the end of the teaser. So, what have we seen today? Well, distributed systems are everywhere, of course. Internet. They're very complex, but you can solve that by looking at a set of core problems and solving those. And so the real big systems are built out of core algorithms. I mentioned two: consensus, broadcast. Atomic broadcast is equivalent to consensus. But there are other forms of broadcast that are not equivalent to consensus. Leader election and other kinds of algorithms. Shared memory, like databases. Okay? Core. And we will see these algorithms. Third point, the principal distributed system in the world, there's many of course, but many of them are built on top of the internet. And the internet is a partial of the system. And we will talk about that a lot. Another point is failure. There's many different kinds of failure. I mentioned three here: crashes, Byzantine, and self-stabilizing. But there are other kinds of failure, like a disk, like a computer. When your computer fails, question?
Is the token ring problem the same as the philosopher's bread problem, or is that totally different?
No. It's very different. You're talking about dining philosophers.
Yes.
Well, the dining philosophers is basically a resource allocation problem. Two philosophers, they want to use the fork. And how do you make it fair? So you have 5 philosophers around the table, sitting around the table, and you have 5 forks. And each philosopher needs 2 forks to eat. But there's only 5 forks. So if I take this fork, the guy next to me cannot eat. So the idea is you want to make a fair algorithm where no philosopher will starve. Okay? So this is actually much more complex than token ring, where the token, you could implement philosopher using token ring, because when the philosopher gets the token, he's allowed to eat. That's the idea, right?
I mean, in token ring, the token has to pass through all the nodes.
Yeah, it will go, let's say you have 5 philosophers in your ring. When a philosopher gets a token, he's allowed to eat. But it means only one philosopher can eat at the same time, even though you have 5 forks. So it's not as efficient, because you could actually have 2 philosophers eating, right? With 5 forks? Couldn't you? Yes, you could, But with token ring, you would have only 1 eating. So you could solve dying philosophers using token ring, but there's many other solutions. Okay. So, but I don't want to talk about dying philosophers, but it's, yeah. Okay. This is a good question. Yeah. So the token ring, so it's basically a resource allocation, If I have the Ethernet and 2 nodes want to communicate, which one can do it? If they both do it at the same time, then there will be garbage on the Ethernet. So there has to be a conflict resolution. The Ethernet uses like a random algorithm, where each node waits a random amount of time. But token ring uses a deterministic algorithm, where the token goes around. Turns out Ethernet won, okay? Oh, Token Ring is probably still used inside of IBM, because IBM invented it, okay? So they will still like it. But somehow it didn't get used so much in the external world, for various reasons. I'm not an expert on the reason why. Yeah? Okay, and the final thing we see, this is the whole second half of the course, we're going to talk about large distributed systems. So the first half of the course will be very formal. We'll see lots of code, and we'll prove correctness using the models, these three models, okay? Asynchronous, partially synchronous, and synchronous. If you buy a cluster, you will be here. If you write internet, you will be here. Yeah, question?
Just which language we'll use throughout the course.
There will be the course slides uses a formal model, which is basically an event message passing model. So the model of this book is what we're going to use, which is a model where we will start seeing it next week, where you have each node is running a small piece of sequential code, and it can send messages and retrieve messages. So it's basically a message passing.
Is it a formal language? Or
Yeah, it's a formal language which we will use to prove the correctness. But in the practical project of the course, we will use a language called Erlang, which also does message passing. So in fact, when you learn the formal model of the course, in some ways it's very close to Erlang, even though it's formal. Erlang is not a formal practical language. So the formal model of the course will be a distributed event message passing model that we will use. It's by far the best model. If you want to define complicated algorithms with partial failure, concurrency, or partially synchronous, that's not so simple, okay? In this model, it's probably as simple as it can get, okay? So it's a really good model for distributed algorithms. And actually, Erlang is actually quite close to this. So that means in the project, you will be implementing some distributed algorithms that we see in the course, in a real system.
And I guess we'll learn Erlang.
You'll learn it. We'll teach you. But it's based on the model. But if you have followed one of my programming courses, you've already had an introduction to message passing, to Erlang, okay? But even if you have not, we will use a message passing model for all of our algorithm definitions in this course. So if you want to succeed the course, you have to learn that model, okay? But it's the best model that I know. It's really useful. And with that model, you can write concurrent failing systems, which I do not recommend that you write in Java, for example. Okay? I really do not. With the model we use, we can actually prove these algorithms correct. So it's the best that I know for writing distributed algorithms. Okay, maybe I stop here. I think we're, let's start, but we start next week, yeah? Next week, Wednesday, and next week we will start by giving some formal definitions, okay? Okay, so please connect to the Moodle, huh? The Moodle is very important if you're not yet there, huh?